Today I will build a neural network from scratch in C++. By the end of this video, we will have a neural network that can recognize handwritten digits. For example, if we input an image of the number 4, it will tell us it's a 4. Or if we give it an image of the number 9, it will output it's a 9. And so on. So, what exactly is a neural network? A neural network is made up of layers of neurons. In our example, we have 5 layers. Each neuron in one layer connects to every neuron in the next layer. And these connections, represented by lines, are called weights. This structure repeats across all the layers. The first layer is known as the input layer. This is where we feed in our data. All the layers in between, except the last one, are called hidden layers. And the last layer is the output layer. This is where we get our result. But how do we actually input data into the neural network and get an output? We start by assigning values to the neurons in the input layer. Then calculate the values for the neurons in the following layer. We continue this process layer by layer until we reach the output. This process is called forward propagation. Let's break down forward propagation with a simple example. Imagine we have a neural network with an input layer of 3 neurons and just 1 neuron in the output layer. To calculate the output, we multiply each input by its corresponding weight and sum up the results. But there is an issue. The output is constrained to pass through the origin, the vector of zeros, which can limit how well the model fits the data. To fix this, we add something called a bias term, which helps shift the output. Let me explain it more clearly. Picture a neural network with just 1 input neuron and 1 output neuron. On a 2D plane, we can plot data points like circles and balls, and our goal is to draw a line that separates them. Without the bias term, the line will always go through the origin, no matter how much we adjust the weights. This makes it impossible to properly shift the line to separate the data. By adding a bias term, we can shift the line up or down, giving us more control over its position. This extra flexibility helps us separate the circles and balls more effectively. With the bias, our output function looks like this. Now we can create a line that better separates different types of data. The last piece of the puzzle is the activation function. The activation function is key because it introduces nonlinearity into the model. Without it, even with multiple layers, the network would only be able to model simple linear relationships. Some common activation functions are the sigmoid function, ReLU, and the hyperbolic tangent. Each of these functions transform the neuron outputs in unique ways, helping the network learn diverse patterns and improve its predictions. In this video, we will use the sigmoid function as our activation. Since we've already explained forward propagation, let's now move on to a more complex example with a larger neural network. As before, we compute the outputs for each neuron in the layer. In this case, we can represent our calculations using matrices. The weights and input values will be organized into matrices, allowing us to compute the outputs through matrix multiplication. After computing the weighted sums, we will apply the activation function to the resulting matrix to obtain the final outputs. Let's dive into the code. The layer class consists of a matrix of weights, a vector of biases, a vector for the output, another vector for the activated output, and the activation function. The matrix of weights has dimensions corresponding to the number of inputs by the number of neurons in the current layer and is initialized randomly. The vector of biases is the size of the number of neurons in the current layer and starts as a zero vector. The forward function handles the calculations. The output is compute as I described before, and the activated output is obtained by applying an activation function to the raw output. The neural network class consists of a vector of layers. The forward function iterates through each layer and applies the forward function from the layer class to compute the output for that layer. Finally, the output of the neural network is the activated output from the last layer, representing the network's prediction. Now, let's talk about the error function. When we feed an input into the neural network, it produces an output. The error function then calculates the difference between the network's predicted output and the actual target value. This error function quantifies how far the network's output is from the target and serves as a key measure of the model's performance. The goal of training is to minimize this error over time. For our purposes, we will use the mean-squared error function. Once we have calculated the error, the next step is to use it to improve the neural network's performance. This is where training comes in. During training, we adjust the weights and biases to minimize the error. The process used to make these adjustments is called backpropagation. Backpropagation works by calculating how much each weight in the network contributed to the error. Then, using an optimization algorithm like gradient descent, we update the weights and biases in the direction that reduces the error. This iterative process is what allows the network to learn from its mistakes and improve over time. The calculations for updating weights differ between the output layer and the hidden layers. We first explain the calculations for the output layer, and then, as the name suggests, we work our way backward to the first layer. To calculate how the error changes with respect to the weights in the output layer, we apply the chain rule. As shown by the arrows, we first calculate the change of the error function with respect to the activated output, then the change of the activated output with respect to the raw output, and finally the change of the raw output with respect to the weight. This step-by-step process allows us to determine how weight affects the overall error. With this breakdown, we can now easily compute each of these components. We can write similar equations for every weight in the output layer. Noticing that certain terms appear repeatedly across different equations, we introduce a term called delta to represent this shared component. Now, we can represent the entire process using matrix operations, where we multiply the input vector by the transpose of the delta vector. To calculate how the error changes with respect to the weights in the hidden layers, we apply the chain rule once again and reuse some of the calculations from before. The process is similar, but here we observe that changes in the activated neuron in the hidden layer will impact each output neuron in the output layer. Using the chain rule as the arrows show, We first calculate the change of each element of the sum in the error function with respect to the activated output of the hidden layer. Then we calculate the change of the activated output with respect to the raw output. And finally, the change of the raw output with respect to the weight. This gives us the necessary components to update the weights in the hidden layers. To calculate the first element, we apply the chain rule again. We observe that this element is the same as our delta from previous calculations, so we can set it as delta. The second element follows a similar pattern. And the remaining steps are straightforward computations. For each weight in this layer, we can write similar equations. Just as we did in the output layer, we introduce a new variable, delta, to better illustrate the common terms and simplify the notation. The final step is to represent this process using matrix operations. Let's take another look at the code. We've added the necessary calculations for the sigmoid function, the error function and their derivatives. These functions are essential for the backpropagation process. In the layer class, we've also introduced the derivative of the activation function and a vector for delta, which will be crucial for calculating weight updates during backpropagation. Additionally, we've implemented a function to update the weights and biases, as I mentioned earlier when discussing the gradient descent algorithm. In the neural network class, we've added a backward function which implements the backpropagation process. First, we calculate the delta for the output layer. And then, moving backwards through the network, we calculate the delta for each hidden layer. Finally, we iterate through the layers and update the weights and biases. The final piece of our project is the dataset. We will be using the MNIST dataset to train and test our neural network. MNIST is a widely used benchmark in the machine learning community, consisting of 60,000 training images and 10,000 test images of handwritten digits. Let's break down what each image looks like. Each image is a square with dimensions of 28 by 28 pixels, making up a total of 784 pixels. Each pixel holds a value between 0 and 255, where 0 represents black and 255 represents white. For our neural network, the input will be a vector of 784 neurons, each corresponding to a pixel's normalized value, a value divided by 255. We can customize the number of hidden layers and neurons, but in the code we will be using one hidden layer with 64 neurons. The output layer will have 10 neurons, each representing one of the digits from 0 to 9. And that's it. We've covered all the essential components needed to train and test a neural network. Now, let's go over the code that reads the data, trains the neural network and tests its performance. To load the training data images, we first read the initial 16 bytes, which contain the file's metadata, such as the number of images, and then load the 60,000 images into our data vector. Similarly, for the training labels, we read the first 8 bytes of metadata and load the 60,000 labels. We apply the same process for the test data, reading both the test images and the test labels. In the neural network class, we've added a train function that performs training on the training images for a specified number of epochs. During each epoch, the function iterates through each image, performing forward propagation, calculating the error function, and then executing backward propagation. After each training step, we print the loss to monitor the model's progress. We've also implemented the test function, which iterates through the test images. For each image, the function performs forward propagation and counts the number of correct predictions. At the end, it prints the accuracy of the model. The last step is to execute these functions. First, we read in the training and test data. Next, we create a neural network with one hidden layer containing 64 neurons and an output layer with 10 neurons. Note that, as per our implementation of the layer class, we don't need an explicit input layer. Instead, we treat the image data as the input layer. We then initialize the neural network with these layers and apply the train function, specifying the learning rate and the number of epochs. After training is complete, we use the test function to evaluate the network's performance. Welcome to the end of the video. We've successfully implemented the neural network from scratch. Now, let's run it and see how accurate our model is. As you can see, with each epoch, the loss decreases, indicating that the neural network is learning and improving. The accuracy reaches around 95%. I believe with a few small adjustments, such as changing the activation function in the hidden layer to ReLU and in the output layer to softmax, we could push the accuracy even higher, possibly to 97%. Thanks for watching.